Our second example of a three-dimensional dynamical system is one that should be familiar to anyone who's taken a course in freshman physics, the periodically driven damped pendulum. So what is this system? So let's imagine a pendulum hanging in gravity. So here is a mass. There is a rigid rod that's holding it to a pivot point. We characterize the pendulum by its angle with respect to the vertical. There is a gravitational force G that is pointing downward, trying to bring it to rest. There is an oscillating driving force of magnitude gamma omega naught squared. I'll define these quantities in just a moment, but that's trying to jiggle the pendulum. And furthermore, there is friction at the pivot point. So under the combination of gravity, which is trying to make the pendulum oscillate back and forth, and periodic driving force, which is also trying to make the pendulum move back and forth, and friction, the question we want to understand is what happens. So first of all, let's write down the equation of motion. And again, for anyone who's taken a basic physics course, this equation will look very familiar. The equation of motion is phi double dot plus 2 beta phi dot plus omega naught squared sine phi is equal to gamma omega naught squared cosine omega t. So in this equation of motion, omega naught is the natural frequency of the pendulum in the absence of friction or a driving force. Gamma is a dimensionless measure of the strength of the driving, and beta is a measure of the friction. And here omega is the frequency of the driving force itself. And I'm going to choose for simplicity that omega is equal to 2 pi, which means that the period of the driving force is equal to 1. So every 1 second, the driving force goes through a single cycle. For those who have taken a basic physics course, this equation looks familiar, but the crucial point is that it doesn't look like a dynamical system because it's not a first-order system. But as mentioned in one of the very earliest lectures, any higher dimensional time-dependent system can be recast as a dynamical system by suitably defining variables, by going to a higher dimensional space. To recast this as a dynamical system, let us define phi. That's just the good old angular position. Let me define phi dot as the angular momentum. So I'm either ignoring units or I'm choosing units such that the mass of the pendulum and the length of the pendulum itself are equal to 1. And let me define a new variable z that's equal to omega t. So this single second-order differential equation can be recast as a system of 3 first-order differential equations, namely p dot plus 2 beta p plus omega naught squared sine phi is equal to gamma omega naught squared cosine of z. Phi dot angular momentum, that's equal to p. Phi dot is equal to p, and z dot is equal to omega. So this is now a 3-variable system, first order, autonomous because there's no time on the right-hand side. So we can recast the second-order differential equation as a 3-dimensional dynamical system. Unfortunately, this is much more complicated mathematically than the 3-dimensional system we just discussed, namely the 3-species model. So basically, we cannot make any analytical progress in analyzing this equation of motion in this way. So what I want to do in the remaining part of this presentation is just to give you an empirical guide to what is the behavior of the system as a function of the single driving parameter in the system, namely the magnitude of the driving force, and to show some of the beautiful behaviors that actually emerge for this simple system.